I mean, I have a microphone, so I feel like that'll work pretty effectively. All right, can everyone hear me? I think we'll go ahead and get started. I felt like I need an introducer for the introducer, actually. So I'm Scott Hotaling. I'm a new faculty member in Watershed Sciences. So I've only been here for a couple of months, and I'm still getting to know all of you, especially across the college, but it's really nice to see you. I am excited to introduce Adrian Harpold, who I first met back in 2018 at a mountain research conference, but I've been a fan of his work and citing it for a lot longer. Dr. Harpold he got his PhD in 2010 from Cornell, and then he did a couple of postdoc positions in the West, the University of Arizona and University of Colorado in Boulder, before taking a faculty job at Nevada, Reno in what year?
2014.
Okay, so he's been there for about 8 years, where his lab focuses on mountain ecohydrology and a lot of other really important questions with water in the West. So with that, I'll turn it over to Adrian.
Thank you, Scott. Give this back to Thad. Yeah, you guys can hear me okay? So you guys are lucky to have Scott. Maybe I know him better than a lot of people here, but it's really an honor to be here, to be invited by the graduate students. Yeah, just nice to be back talking science in person, and hopefully having lots of great exchanges with you all. What I would like to talk about is the water cycle in the mountains. I'm a hydrologist. I think about water flow, water storage, and I'm going to make the case today that the mountains are disproportionately important for our water supplies and therefore become really important for how we're going to manage water in a changing climate. I've learned to do some of these things at the beginning rather than at the end because as all of our, the faculty and PIs in the room understand, like our teams do a lot of this work, and it seems like we don't often give them enough credit, but 8 years into my position at UNR, I've had really incredible students. I've had several really excellent postdocs, and I've got to work with people all over the country. It's some of my favorite people in institutions, and had quite a bit of mentoring from people I really look up to. So I put their names on the screen because I really appreciate. No, it is. I'm just not pointing. Oh yeah, I need to be here to be in the. Yeah, okay. I think if I'm over here, I'm in the movie up on the screen. All right. So what are we going to talk about today? I want to make 3 points for you, and there's going to be a lot of details here, but the things I want you to take away from this is that climate change is having big effects in the mountains, and we aren't predicting the consequences of that with probably the certainty that we need. And vegetation plays a large role in the mountain water cycle. Sometimes we look at these big mountains and, we see the tops of the peak, we see all the snow, but, in the Sierras, in the Wasatch, in the Colorado Rockies, there are forests and vegetation on almost every slope. And how this vegetation is going to respond to climate change from a water balance standpoint is a very pressing question in the Western US in particular. And vegetation management really becomes our big tool to manage water in these mountain systems. And I'll get into this some today. I am fortunate to give another talk 24 hours from now that will really focus on the sort of applied forest management side of this work, but we'll touch on it a bit today. So this is a stylized photograph of Dana Meadows in Yosemite National Park. I could have picked many locations that have mountains above tree line with snow on them, conifer forests. So does this work? Yeah, I'm getting used to this clicker here. Grasslands and wet meadows, dry meadows, diversity of vegetation. And what I want to step us through in this talk is thinking about the changes to these systems from climate change, how the vegetation and the ecosystems may respond to that, or our understanding of what we know and what we don't know. And then how do we manage these systems for the benefit of the ecosystem as well as water supplies? And what I'm going to do at the beginning of this talk, if the clicker works here, is take us through what I see as some of the large, important changes in these mountain ecosystems that are resulting from climate change. So changes in temperature, changes in vapor pressure or humidity, wind and precipitation, and then quite a bit about snow. So shifts in snow lines and albedo. So the picture I'm trying to paint for you all is that climate change in the mountains is multifaceted, it's complex, it's not just the air temperature is going to get warmer. But the air temperature is going to get warmer. And one of the interesting consequences of that is there's an expectation that at higher elevations, we're going to get greater warming. So this idea of elevation dependent warming. Pretty good evidence that this is happening. It's particularly happening in the winter months, December, January, February. So this is showing elevation and the temperature trend. Man, I'm really struggling with that. And it's showing that at the higher elevations, there's larger changes in temperature, larger effects in winter. So the mountains, just like a lot of the polar areas, are particularly at risk because of some of the physical feedbacks of climate change on temperature. So elevation-dependent warming. Another not unique concern to the mountains, but certainly something that has really wide implications for future hydrology is the snow albedo feedback. Albedo is effectively how much the fraction of incoming sunlight or solar radiation that is going to get reflected back. If you have low albedo, like this dirty snow here in the top right, you can have a major, so 50% reduction in albedo compared to clean snow. And that means that 50% more of that incoming solar radiation is going to get absorbed by the land surface. So that has implications for temperature, everything else being equal. Abigail, I think that's supposed to say Swan. Abigail Swan is showing that just a small change in albedo, so not this drastic, but from 0.3 to 0.1 is equivalent to changing the surface air temperature by about 5 degrees. So these direct feedbacks by losing snow, absorbing more radiation, warming the system, that is the snow albedo feedback. And we'll come back to this in terms of its consequences for water balance and water. But right now I'm painting the picture of these different changes. Okay, well, hopefully you all have seen some of this before. I felt a little bit like I was preparing one of my undergrad lectures here, but I do feel like understanding some of these concepts is really, it's critical. Even if you don't work in this field, even if this isn't something that is your day to day, I think understanding these impacts of climate change are important since we're all living through this. This is the Clausius-Clapeyron relationship, or the saturated vapor pressure curve. So what it's telling us is the saturated vapor pressure is that blue line, how it varies with temperature. It's telling us how much water vapor could be in an air mass for a given temperature. So if you follow that line, you have a relative humidity of 100%. If you're below that blue line, you have a relative humidity below 100%. If you're above that blue line, you have a relative humidity above 100%. So you can condense water. The real take home here is that this is not a straight line, right? This is not a linear relationship. As you get warmer, you have exponentially more, well, the saturated vapor pressure responds exponentially. And this has really important implications. For warming, we're moving to the right. So the air mass, everything else being equal, could have more water vapor in a saturated state. So this really has two implications. It has implications for not having enough water vapor and being unsaturated, causing sort of more severe drought symptoms, but there's also implications for being supersaturated. If you're below that line, you have a vapor pressure deficit. And effectively, the way to think about this is vapor pressure deficit is going to go exponentially with temperature. So the warmer you are, if you have the same amount of water vapor, you're going to have exponentially higher vapor pressure deficit. Vapor pressure deficit is one of the key ingredients you need to evaporate water. If you don't have a vapor pressure deficit, you can't evaporate water. Conversely, the larger vapor pressure deficit you have, the more potential you have to evaporate water. So what does this mean? It means that the ring width index, or you can think of this as basically how effective trees are growing across all these regions of the Western US, from the Pacific Northwest down to the Southwest here in red. They all show much more negative sensitivity to vapor pressure deficit than they do temperature. So these systems are responding negatively to increases in vapor pressure deficit, effectively because the vegetation is water stressed and it has to slow down its photosynthesis. Fire has a similar behavior. Effectively, the higher the vapor pressure deficit, the more extreme the fire behavior is, and the more you can desiccate and lower the fuel moisture. So this relationship isn't quite as extreme. This is from a paper by Park Williams, but you can see that there's a stronger relationship between the size of fires in California with vapor pressure deficit than there is with air temperature on the right. So this Clausius-Clapeyron relationship has really big implications for more evaporation-related stresses on ecosystems. The converse of that is being in this supersaturated region here. So now we've warmed the atmosphere from climate change, but we're up in the atmosphere. Maybe we're close to the ocean. There's enough water where we can supersaturate. Supersaturation is a requirement for precipitation. You need that extra moisture in the atmosphere. We all like precipitation in the West, right? We all, I think, feel a little desiccated sometimes. But the concern, especially in places like California that I'm showing you here, it's a little hard to see, but this is the California. This was working so much better when I was practicing. This is the California coast. This is the Sierra Nevada. I live like right there. And it's showing historical atmospheric river events in the left panel, future precipitation expectations in the center panel, and the difference between the two in the rightmost panels. And it's indicating with physical modeling, this is a paper by Daniel Swain and colleagues, that both the total winter precipitation is expected to increase and the most intense peak hourly precipitation is expected to increase. And you can see the bullseye is right along the Sierra crest here, which is the water supply for most of California. So we're lucky that we get both more extreme wet and more extreme dry out of the saturated vapor pressure curve. I think this is sometimes people overlook this feedback that occurs as a function of climate change, but from a water resources point of view, we kind of have the worst of both worlds, right? We have more extreme droughts, hard to manage, more extreme precipitation, also hard to manage. Oh, I was told this will come back in 2 seconds. Another important feedback in mountain systems is the lifting of precipitation over topography, which we call orographics or orographic precipitation. A really nice study by Charlie Luce and colleagues was trying to explain why across the Pacific Northwest do we see major decreases in the red outlines here are stream flow in these watershed boundaries, and then the dots are precipitation gauges. And the quick take home is Precipitation, kind of a mixed bag, but we see big decreases in streamflow. And they, in a really clever study, it must have been, it's in Science, they were able to infer that the changes are because we are not getting the lift of those air masses over the mountains because of a decrease in wind speed. And therefore, we're not getting as much, stream flow in our watersheds. But one of the riddles of this that's pretty interesting is the reason you don't see a lot of changes in the precipitation gauges is because they're all in the lower valleys. We don't tend to measure precipitation up on top of the mountains. Oops. Can I? Yeah, I can go back. I think I was done here. So another feedback with the effects of climate change on this are a little hard to understand. We don't have a good sense of how wind might change in the future, but clearly a unique effect on mountain systems. Okay, maybe the more intuitive pieces now. I started with maybe the harder conceptual things. What used to fall as snow is probably going to fall as rain. This is a figure by Zion Klaus showing end of 20th century versus sort of middle of 21st century comparisons. And we're talking about sort of Januaries that used to be 50 plus, this is across the entire Western US. Januaries that used to be 50+% snow are going to be 25% snow by mid-century. Big changes, right? Big changes. We all know that one storm, is very different if it falls as snow or falls as rain. So we're talking about major changes across most of the mountain ranges in the West. Hydrologically, what does this mean? Well, it means that what was getting stored and melted later is now falling as liquid water. So we are going to get the intensity of our precipitation changing. We were buffered, our intensity was buffered by snowmelt. In the future, we're going to have a much more mixed bag where some places like these diamonds here that are mainly focused on the West Coast could see an increase in the intensity of precipitation. Other places, these stars that actually are kind of close to us here, may actually see decreases in the intensity of precipitation because they used to get big snowpacks that actually would melt more intensely than the rain. So really a mixed bag, especially at the shorter timescales. At the longer timescales, so if you think about how much water is going in over 30 days, everything is really slowing. So we're going to get, as we shift from snow to rain, we're probably going to get slower input rates. What is that going to do to our ecosystems, our mountain ecosystems? I'll come back to that in a second. This is a paper by Keith Musselman from Nature Climate Change in 2017. Very catchy title, Slower Snowmelt in a Warmer World. Why do we expect to get a slower snowmelt in a warmer world? Well, it's because we're shifting the snowmelt earlier in the year, we'll say on the order of weeks. When we go earlier in the year in almost all these systems, we have a lower sun angle, right? We have less radiation coming into the system. So the snowmelt starts earlier, but there's less energy to melt it because it's starting earlier. And you really see this most dramatically at the very highest melt rates, the very deepest, latest melting snowpacks. They are the places we expect to really slow down. Some of the lower melt rates are in green, suggesting they might actually get faster. All the browner colors are suggesting slower. So slower melt rates because of earlier melt timing. That is kind of the spring melt that we sort of typically have seen starting in March and April. But we also experience these intermittent melt events in the winter, especially in a place like the Sierra Nevada that's quite warm. The snowpack is close to isothermal, close to 0 degrees C, and it can have these small melt events throughout the winter. We did an analysis of this across the SNOTEL network in the Western US, and we showed a lot of variability in trends. So the red colors are more winter ablation trends over time. And you can see the hotspot is really up in the Pacific Northwest. So what is going on with this? We were able to empirically show that places that were more humid, more water vapor in the air, they were much more sensitive to warming temperature and higher ablation rates than places with lower humidity. And we're back to our saturated vapor pressure curve. You guys know what you're looking at, right? The black line is the saturated vapor pressure. We're looking at it in terms of absolute humidity now. It's just a different way to calculate humidity. The blue is the southwestern US, kind of Arizona, New Mexico. The red is the Pacific Northwest, like the Cascades. So you can have snowpacks that effectively have the same winter temperature, but the arid, low humidity ones are not melting in the winter, and the higher humidity ones are melting in the winter. So you're going to get this large regional pattern that really comes out of the local hydroclimate. And now we're going to take it a little bit more into the hydrology, less out of the climate, and think about, well, what does this mean for water coming into the system, for ecosystems' ability to use it? We tend to have seasonal snowpacks that form early in the winter. They begin to melt kind of mid, late winter. And then once the snow melts, you have this sort of long recession as the water drains out of the system. Maybe we get a couple of summer rainfall events that bring the soil moisture back up, but we effectively have this one large unimodal response, the freshet, they call it. If we move into an ephemeral snowpack that's coming and going, melting in the winter, or more rain-dominated system, we lose that synchrony between water and energy, and we're effectively getting water inputs that are more synchronized with precipitation. So before, we had this system that was very well behaved, where when snow disappeared, we hit our peak soil moisture for that year. This is several thousand years of measurements across all of the Western US, a very strong one-to-one relationship. You lose the snow, that's the wettest the soil moisture is for the whole year, and then it starts to dry. If we move to a system that's melting more in the winter, the snow's coming and going, we lose this timing synchrony that has been there for at least the recent historical period. All right, let me check my time. So part two, we have complicated changes. That's what I'm sure I gave you the complicated part. So hopefully you picked up something new in that. We have these changes to the hydroclimate from climate change. They're complex. They're going to have different effects in different places. What does this mean for hydrology, for water resources, for water planning? Well, I am a hydrologist, so we like our water budgets. That's it's better than my personal budget. Yeah, it's much more, it tends to add up better. So the simplest way that we think about a lot of this is precipitation is your only input. So that's on one side of the equation. And your outputs to it are Q, which is stream flow. So the amount of surface water. ET, evapotranspiration, so that's water vapor leaving the land surface back to the atmosphere. And then you have storage and groundwater, typically in the subsurface. And those tend to be thought of as smaller terms. So if we go back to the Sierra Nevada and we think about the water budget in, say, a place like Yosemite National Park, Dana Meadows, this is very typical of mountains in the West, where you have lower elevations. On the left side of this panel, those lower elevations get less precipitation because of orographic lift, right? The lifting of the water over the mountain range puts more precipitation up at the top, at the higher elevations. You tend to have a lot of evapotranspiration, but your maximum tends to actually be at a mid elevation. This is specific to the Sierras, but typical of other places. And then you see this fall off in the evapotranspiration. So you have this very uneven distribution of precipitation and an uneven and different distribution of evapotranspiration. The blue line here that I'll come back to is differencing the two. So if you take precipitation minus evapotranspiration, which is effectively the excess water, you get something that looks like this, with most of the excess water at the highest elevations, which is what I'm showing here. So why do we see these characteristic patterns of, we explained the precipitation one with orographic lift, but these characteristic patterns of the water budget? One way that hydrologists, really this gentleman Budiko from Russian climatologist has really helped us think about this, is the linkages between energy and water. So this relationship is effectively energy divided by the precipitation. So potential evapotranspiration is the potential to evaporate water if all the incoming energy went to evaporation, divided by precipitation. So if you're less than 1, there's more water than you can evaporate with the energy that's available. If you're greater than 1, there's more energy than there is water to evaporate. The vertical y-axis is evaporative index, evaporative fraction. So this is how much of the precipitation was evapotranspiration. Here it says actual evapotranspiration divided by precipitation. So you can't have a value larger than 1, because that means that all your precipitation is evaporating. And obviously you can't have a value lower than 0. I won't go into the energy limit here, but the point is that as you are more energy limited in this corner, you are evaporating less water. And as you move to the right and you have more energy as a function of precipitation, you evaporate more and more water. So if we go back to our Sierra Nevadas here, at the lowest elevations, where'd it go? At the lowest elevations, we are sort of on the right side of our Budiko. We're very dry, and all of the precipitation in black is getting evaporated in green, right? Those lines are very close. At some point, the vegetation is shifting from water limited to energy limited. And as we go to the right side of this figure, we are effectively moving to the left side of the Budiko, and we don't have as much energy to evaporate the water, and we have much lower evapotranspiration. So this is typical of mountain ranges. We get more precipitation on top, more evapotranspiration at low to mid elevations, which makes these higher elevations our water supply areas, our water towers, sometimes they're called. And that's all interesting to people like me that are hydrologists, but there are real ecosystem implications of this too. This is work by Julia Jones, where they took all the LTER, long-term ecological research sites, they plotted them in the space. As you can see, the ecosystems change, right? If you're out here and you're water limited, you're a desert. You know, as you get to sort of the water energy equilibrium, you tend to be savannas and things like that. And then these energy limited systems are temperate forests, wet forests, boreal forests, and eventually tundra and things like that. So if we think about shifting this around, we're not just talking about the water balance, right? The whole ecosystem is effectively evolved to that water energy environment. Okay, so what do I want to talk about in terms of changes in the water balance in mountain systems? Wind and snow, changes in vegetation cover, both more vegetation from things like encroachment, but also disturbance. Obviously, transpiration, evapotranspiration is a huge part of the mountain water budget. And we'll spend the end of the talk kind of thinking about disturbance and management. I like snow and forests. I feel like that's when I knew that I had found something good for myself when I realized my career was going to take me into snowy forests. Snow processes in forests are actually really complex. And those of you that are skiers and snowshoers probably know this, right? You walk around in the forest up here and the snow is deep in some places, it's shallow in other places. There's just a lot of variability. And that's because we have sort of compensating or conflicting processes that I'll talk some more about. The general sort of idea from these synthesis papers by Andres Varhola is that as you get more forest cover, so kind of towards the right here, or less forest cover to the left, you get more snow accumulating. And as you get more forest cover, you get a faster melt rate. So forest, vegetation, reduce snow accumulation, but increase the melt rate is the general rule of thumb. If you go out on a landscape, like the example I said about walking around, it's actually quite a bit more complex than a simple relationship could predict. If you walk around on Niwot Ridge up above Boulder, Colorado, you can see all sorts of patterns here, right? Patterns that are indicative of wind redistribution, of sublimation or vaporization of the snowpack that look more like the solar radiation onto the snowpack, and then these effects of interception. So within a very small distance of the same climate, same elevation, effectively the same snowpack, you have different effects of the forest depending on the forest structure and its climate. Yeah, I was going to spend some time talking about LiDAR and what we can do with that. But if you're interested in some of this, my talk tomorrow will probably have a large focus on this. An underappreciated part of the mountain water cycle is snow ability to be blown around. This has two big implications. You can move snow from a place different than where it fell. So in this example here, you can see that snow is probably blowing from the alpine areas, particularly down into the valleys, or at finer scales, maybe it's scouring around some of the terrain and redepositing it on the leeward side. And another important aspect of this is that once you get that snow up into suspension, it's very good at sublimating or becoming water vapor and never getting to the ground. So this blowing snow part of the water cycle is really critical in mountain areas, and vegetation has a large impact because vegetation massively changes wind fields. So you'll tend to get, I mean, it's a little bit of cause and effect, but if you have vegetation, it can act as a wind fence and retain that snow. And then you'll often see, wet sort of loving vegetation like aspen, growing in these kinds of snowdrifts preferentially. Interception is water that falls into the canopy, that gets held in the canopy and evaporates or sublimates, never makes it to the ground. These can be very large numbers in dense canopy like spruce forest, where 40% of the falling precipitation gets caught in the canopy. If snow shifts to rain, rain is much less effectively intercepted, right? Because rain can go through needles, it can drip to the ground. Snow will bridge across needles, it'll get held up in the canopy. This can be a large part of a mountain water budget, is snow interception. So one of the aspects to the future of snow and mountain systems is really how the snow is going to interact with the vegetation that's there. Again, the patterns of vegetation and snow are really complex. You can see on the front edge of this, the snow is melted earlier, but if you look back into the forest, you still see snow under the canopy. There's a lot of variability. What we see, and I'll show a little bit of this on the next slide too, is that the climate really controls how snow interacts with the forest. In a warm climate, like the top panel, which is from the Sierra Nevadas, you get more snow in the open, which are the circles, than the triangles. It has to do with long wave radiation back off the tree, some radiation effects that I won't get into too much. In colder environments, you see more snow under the tree than in the open. You know, sort of same everything else, same kind of amount of precipitation. The climate will control how the snow disappears in similar forests. You can take that and you can put it on south-facing and north-facing hill slopes, high vegetation density and low vegetation density, right? Dense canopies, open canopies, and you can start to think about the complexities that snow-forest interactions might have on a landscape. And this is something my group has thought quite a bit about. There's still not a really well-accepted model to predict how snow will accumulate and ablate across different mountain climates. A pretty big unknown. And this is something I'll talk a bit, kind of go into more detail tomorrow, because the talk tomorrow will really be focused on how could we manage forest for beneficial snow and water. So one of the questions that arises is, how will evapotranspiration change in these mountain systems? I made the case that the higher elevations, these are our water towers, not as much evapotranspiration, more precipitation. This work by Mike Goulden and Roger Bales and PNAS, they took a system that they calibrated to the past, and then these RCPs are the different warming scenarios, and they're showing how they think evapotranspiration would change in the future. And if you're a water manager in California, this is sort of terrifying, because it's suggesting that these places that have been our water towers that we've really counted on to deliver water down to where people live are going to have a lot more evapotranspiration. And that's because they effectively have more energy. They're less energy limited, right, in the future. But there's really a couple of big ecosystem questions that arise to really make this jump. One is, can the vegetation move up elevation, right? Because that effectively you'd have to get more vegetation in these higher elevations, which historically have been sort of above tree line. That's a whole discussion. There's the soil aspect to it and all of that. And then there's the phenology, the trees' ecological response to these changing environments. And we thought more about that, because I think the question becomes really important of whether forests will be able to use more water. There's more energy. In a simple Boudico framework, these systems should be using more water. The consequences of that, I hope, are pretty clear, because these are such important water supply areas. So we have a lot of different ways that forests use water through the season. In places that receive clear summer rain, or larger amounts of summer rain, you can have this multimodal, this bimodal response in the middle. Systems that are less rain dominated or have this sort of intermittent melt, less snow dominated, have intermittent melt, can be multimodal, where the vegetation turns on and off, and then turns on in a larger pulse before turning off, and then you can see the unimodal. So this is really telling us how vegetation is responding to that energy and water. We did one experiment, so we're going to zoom in now to this little experimental watershed called Seichen Creek that is here just north of Truckee, California. Reno is kind of like right here, so it's about an hour from my office, where we've set up sap flow sensors that are measuring the rate of sap move velocity within a tree next to large towers that are telling us the micrometeorology. That's my former master's student, Ava Cooper, who did all this work. And what Ava did is a really simple, what we called a boundary line analysis. And she was very creative. She added the art to that. So now we have boundary line analysis art. And the idea here is you have taken many years of data and you've combined it into these top panels. And these top panels are telling you effectively what the uppermost rate that the trees can use water for a given temperature, soil moisture, shortwave radiation, and vapor pressure deficit. So those are our 4 controlling factors. Every day you're going to be limited by one of those factors in our analysis, and you can back your way into this boundary line art here, where at the beginning of the season, all the way up in, say, June and July, you have air temperature, vapor pressure limitations. So if the air was warmer, if you had more vapor pressure deficit, you should be able to transpire more. But then you see a very clear shift around mid-July, where the system becomes more soil moisture limited. And Ava did, we're always sort of wishing we had more data, but we had 3 years of data, many trees, 2 different hill slopes. I don't have the citation here, but this paper is published in Ag and Forest Met. The take home here is that there's really clear correspondence between when the system hits its annual maximum transpiration, so it's using the most water, and when the water limitations occur. So the system, in theory, could transpire more water after July, but now it's being limited by not having enough water in the soil. What does this mean for climate? Whoa. All right. What does this mean for climate change? It means that snow is going to get earlier, and the timing of water stress or soil moisture limitations is going to get earlier, and it's also going to get longer. So what we found is effectively a 1-to-1 for every day earlier the snow melts, you get an extra day of that vegetation being limited by soil moisture. So it suggests that it may not be as simple as having more energy into the system, the vegetation being able to correspondingly transpire more water, that there's a timing phenology aspect to this, that the water's not there when the tree would use it. I think I'm going to skip that one for time's sake. I think I have about 5 to 10 minutes here. One of the other important aspects of these feedbacks in mountain systems is feedbacks to atmospheric circulation. This is work by Abigail Swan. What she's showing is in yellow, what if we effectively nuked all the vegetation in California? What would that do to the climate in the rest of the country? It changes the transpiration, right? Because you've effectively eliminated that, but it also changes the atmospheric circulation, which then feeds back onto the climate, which then feeds back onto the ecological response. So in a future where we were to disturb the climate in California, it has these teleconnections with temperature and precipitation and ecological response in the Midwest. So our mountain systems, which are disproportionately a large part of the net primary productivity in the West, has teleconnections, has effects on things well beyond the hydrological boundaries of the system. And I think this work is really important, sometimes hard to bring into applied management, but it really suggests that we could see changes that we don't expect once we go into a world with bigger disturbances. And that's what I want to spend the last couple minutes talking about. What does this mean for management? I'm in a natural resources department, watershed sciences. There's certainly like a research to applications part of this. And I'm an engineer by training, and I like to think about, well, what can we do to make things better? This is a paper by Sarah Goking and Dave Tarboten that is trying to understand the water budget post-disturbance. And this is really what my talk is going to be about tomorrow. If you all are interested in this, I'd encourage you to come. I'll get to do a much deeper dive. But we really want to understand how all these components of evapotranspiration may change, because together their sum really has an impact on, let's say, the water resources that we manage. So Q again is stream flow, river flow. One can imagine, I mean, what they're trying to get across in this graphic is you have a lot of potential interactions between transpiration, sublimation, evaporation that can cause things to respond differently to disturbance. And I would go farther, and this is what I'll get into tomorrow, talking about the type and severity and characteristics of place really controlling a lot of how a system responds. We are moving into a world of mega, right? Mega everything. It's hard, I don't know, it's like hard to have the perspective of how extreme this is. I find this graphic to be really helpful to just like help us understand the sort of exponential increase in fire size and severity. So the two largest fires in California history were last summer, way too close to my house. The first two fires that ever burned across from west to east, burned up over the Sierra Divide from California into Nevada were last summer. We're seeing fires that are much larger, much more severe than we have in the past. What does this mean for water? What does this mean for watershed management? The truth is we don't really know. We don't really have predictive capabilities to say how water will change after these fires. This is a recent paper by Park Williams. I'll draw your eye up to these two top panels here, and it's really showing how we think how their analysis shows stream flow changes as a function of the percent burned area. Maybe not surprising, more burned area, more stream flow. So you're effectively reducing evapotranspiration, increasing stream flow. The more concerning thing as a hydrologist is the scatter in this relationship, right? You can have 80% of your forest burn and effectively have no change and 100% change. And that's not good enough for water resource management. We really need, if we're going to really advise the Yuba Water Authority, which is the basin we were just looking at, we need to give them something more than it might not change, it might go up by 100%. So this is a really, I think, an important, timely area of research I'll talk more about tomorrow. What do we do after the fire? I mean, this isn't really my field of research, but certainly huge hydrological implications, right? Do we go in and do sediment control? Do we let it naturally revegetate? Do we grow things in a greenhouse and then do we go bring them out and put them back? Where do we put them? What's the success of getting those to establish? These are big questions that I think we're going to have to answer as these mountain systems change. Another figure by Sarah Goking, who, for those that don't know, was a PhD student here. She did a big analysis, and her take home was that you're really only going to see more water when you don't have high amounts of evaporative potential. So you can think of these red lines as very sort of arid, the green line as wetter, and it's the green line where they show through their statistical analysis, you get a positive response from mortality, so more stream flow. Other places actually show less stream flow. And there's some intuition to this, right? If we think about our water energy coupling, if you're more arid, you're effectively more close to your potential to use all the water. If you're less arid, you're on the left-hand side of this, there's more water in the system. It's probably not surprising that those are the places that can have a positive response of stream flow. Again, too much noise to really have this be an effective water resources forecasting tool, but Sarah and Dave are starting to tease the signal out of the noise here. I'm really close to wrapping up. Again, something I'll talk a lot about tomorrow is forest restoration. So I make the case often that vegetation is really our one knob on the system to manage water. And we don't want to manage it post fact after giant megafires, right? We want to go out on the landscape proactively. That requires knowing where to go, how to do it, and even better would be to have a prediction of what the outcomes would be before you do it. I'll show this figure again tomorrow, but these are all the forest restoration treatments right around Sage-Hen Creek Experimental Watershed over a decade or so, just trying to give the idea of the amount and complexity of doing landscape scale forest restoration. This is something we've really worked on a lot. I find it to be very place-based. So these results are just from the west shore of Lake Tahoe. But what we've been really trying to do is, some people don't like this term, but just building decision support tools. So building tools that a manager could use at their sort of need and ability to give them information to make decisions. So in this case, what elevations, what aspect would give you the most value from a water standpoint from forest thinning? And we gave them this information. They combined this with information about wildlife and a few other things, and they're using this to make decisions. The Forest Service is making decisions. There's also a whole economy behind this. I don't know if any of you are familiar with the Blue Forest Initiative, but they're actually taking this extra water and using it through water bonds to fund the forest restoration itself. So it's sort of like the self-perpetuating machine. Really, to make that work, you have to have some estimate of how much beneficial water you're getting from these treatments. Again, I'd make the case that we're not quite there yet. All right, this is my last example. So forest restoration often has, thinning, mastication, prescribed fire, human-caused restoration techniques. This is fire restoration, but without a human hand. I've been lucky enough to start working with Gabrielle Borromée, who has been working the last 7 or 8 years in a small, well, it's not that small. It's actually about a third of the Merced River Basin. Come on. So this is the Yosemite Valley. For those that haven't been there, you should go. This is Glacier Point Apron, and the Illilouette Creek is up above Glacier Point Apron. It's an interesting mix of wilderness area and national park, which really kind of puts it in an interesting management area. And there was a very forward-looking park fire ecologist named Jan van Wagendonk, who in the sort of 80s, well, 70s and 80s really pushed for not suppressing fire. So in about 1972, they stopped putting out all the fires in this basin. And what you see as a response is this sort of jigsaw puzzle infilling of lightning-caused fires in the basin. So this basin has basically been allowed to have a natural fire regime for the last 40 years. What happens? Well, the conifers get burned. They often become wet meadows, dry meadows, shrubland. So major changes in the land cover. And what does that do to the hydrologic budget? These are modeled results, but it suggests that evapotranspiration goes down and stream flow is going up as a consequence of this change in vegetation. So really powerful, right? Because it's cheap. You just let the lightning cause the fire and let it burn. A positive hydrological benefit. And the real exciting piece of this is when you go and you talk to the forest ecologists and the wildlife folks, there's this sort of triple win. You get maybe more water, less fire severity, right? I mean, if you're getting these repeat fires, you're not going to have as extreme of fires. and a benefit to wildlife. I just saw a great talk about bat activity in this basin last week. So they're calling this the triple win. But it is, I mean, these are the kind of things I feel like we're looking for in the natural resource world, you know, climate-based solutions that give us multiple benefits. We need all the benefits we can get. This is a figure from the paper. I'd encourage you to go read this paper if you're interested. It's short and easy. Right, so lastly, but not leastly, fire and people. I think we think that this is all new because, you know, we haven't had these extreme fires, but this is a place that I work in the Jemez Mountains of New Mexico. This is a paper that also was in PNAS. I find fascinating. I don't know anything about archaeology, but they did this big study where they went back to the Hemish ruins and they reconstructed all these sites. And they were basically able to show that this ancient culture had 27 uses of fire, a lot of which was basically wildland-urban interface management, right? They were burning things around the edges of their community. They were, you know, basically using low-intensity fire to reduce fire risk. And it also had all these other sort of cultural and agricultural benefits as well. So I think there's, and this is something I'm not an expert in, but I think there's a big renaissance to think about these indigenous practices that were very effective for a long time in these same ecosystems. All right, so to wrap up, we have big tipping point climate changes in the mountains, and they're not simple. It's not that just precipitation is going to get, or I'm sorry, that temperature is going to get warmer and we're going to have bigger fires. It's not that simple. We have topography, we have vegetation change, we have humidity changes, and we really need to put all the pieces together to solve this. Vegetation is a big player in the water budget, and we can't constrain it the way that we need to for water supply management. And because of that, we still don't have fully accepted management practices to promote water supplies and water sustainability. And if you're particularly interested in that last point about forest management and water supplies, that will be the focus of my talk tomorrow. So, oh yeah, I had one more. I'm recruiting a student. This is shameless because I'm in a different graduate department, but I said, I don't care. I'm in the graduate program of hydrologic sciences at UNR. I have amazing colleagues. We're recruiting students. If you're looking, especially for a PhD, think about that. There's ads up online. And with that, I'll take your questions.